welcome to the last lecture on cache memory. So, in this lecture we will be seeing some methods for improving the cache performance. Prior to that, we will look into two examples. So, let us consider a CPU with average CPI as 1.1. Let us assume that an instruction mix like ALU having 50%, load having 15%, store 15%, branch 20%, and assume that a cache miss rate is 1.5% and the miss penalty, that means if there is a miss, what is the time required to bring it from the next level, that is, let us say mean memory is 50 cycles. We need to calculate the effective CPI for a unified L1 cache. We have already seen that using write through and no write allocate. So, we will be using write through method for writing and no write allocate. Along with this, we will be having three more functionalities. We will be calculating with no write buffer. Next, we will be doing with perfect write buffer, and another one we will be doing with realistic write buffer that eliminates 85% of write stalls. So, we will be looking. Let us first calculate the number of memory accesses per instruction. So, when there will be a memory access, there will be a memory access for load and store. So, let us say 1 is for just fetching that instruction. We need to have one cycle, we require one cycle for that, and then 0.15 for load, 15% of load instruction, and 0.15 for store, where we will require memory operation. So, total is coming to 1.3. So, for all memory access, all instruction accesses 1 and 15% for load and 15% for store. Now, percentage read will be how much? Percentage read will be once we are reading a particular instruction, and then again when we are reading, when we are loading a word. So, for 1 for reading every instruction and 0.15 for load instruction, divided by total number of memory accesses per instruction, which is coming down to 88.5%. So, percentage read is 88.5%. Now, coming to percentage writes, for the write we will require this 15% only, 15% divided by 0.13, that is the total number of memory access per instruction. So, now we have found out percentage read, percentage write, and we also know the total number of memory accesses per instruction. Per instruction, what will be the total number of memory accesses? Now, coming to the solution. In the first case, we need to consider where we say that there is no write buffer. So, in this particular case, there will be stall on all writes. So, whenever there is no write buffer, so we are not writing it to a high speed hardware, rather we are writing it back to the main memory or you can say the lower level memory. So, in that case, how do we consider the number of stalls? There will be stalls on all writes. So, the memory stalls per instruction will be 1.3 multiplied by 50 into, we have percentage read of 88.5%, this is percentage write of 11.5%, and assume that there is a cache miss of 1.5%. So, we need to consider that as well. So, if we consider that, and what is 50? 50 is our miss penalty. So, for miss penalty there will be 50 cycles. So, when we multiplied 1.3 into 50 into this percentage, we get roughly 8.33 cycles. This is the total number of cycles that we are getting. That means, these many memory stalls per instruction will be there. So, what will be the CPI? CPI will be average CPI plus we have to consider this memory stalls CPI. So, this memory stalls per instruction is 8.33 we have calculated. So, total CPI will come down when we have no write buffer as 9.43, when we are using write through policy without any no write allocate. Let us see the next case where we have a perfect write buffer. In this particular case, all write stalls are eliminated. So, there will be no write stall now. So, what we need to calculate? So, for writing whatever we have to consider, we need not have to consider that. So, it will be 1.3 multiplied by miss penalty multiplied by the reads, percentage read and the miss rate. We have to multiply these two only, and we are not considering anything for the write. In the previous case, we have considered this 11.5, but here we are not considering that. So, for this it is coming to 0.86 cycles. So, the CPI, when we have a perfect write buffer, we have 1.1 plus 0.86, which is coming to 1.96. So, we can see that there is a huge difference between when we have no write buffer and when we have some write buffer. Now, let us consider a realistic write buffer. So, obviously, the perfect write buffer is difficult to have it, because there might be some writing going on and at the same time some read operation is also required. So, in such cases, if there are 85% of the write stalls are eliminated, that means 15% will still be there, but 85% there will be no write stall. So, in that case, how do we find out? 1.3 into miss penalty multiplied by, this was the read percentage. For the read percentage, it will be 1.5 and there will be 15% for the write. So, let us just see this. This is 11.5% and for this 11.5%, this will be 1.5. This is not 15, this should be 1.5. So, which will come down to, if you solve this particular equation, it will come down to 1.98 cycles. So, it is now coming down to CPI 1.1 plus 1.98, which is roughly equal to 3.08, which is to some extent a realistic value, because we will definitely have some, even if we have write buffer, there will be some stalls. So, now let us consider another example where we have similar kind of values, but now we have to calculate the effective CPI for an unified L1 cache using write back and write allocate. That means, we will not be writing it through to the main memory always, rather we will be writing it into the cache memory with write allocate. That means, we must have a space in our cache memory to write that particular thing. With a probability of cache block being dirty is 10%, and we assume that 10% of the time the cache block will be dirty, and if the cache block is dirty, we know what we need to do it. In that particular case, we have to write back the data into the main memory, and then we have to again read or write whatever we need to do the next. So, the number of memory accesses per instruction will be 1 plus 0.15 plus 0.15, that is 1.3. Now, let us see the memory accesses per instruction, which is 1.3. Stalls per accesses will be 1 minus hit ratio of L1 into TMM into percentage time it is clean because when it is clean, then we have to only write it once. If it is dirty, then we have to do it twice. We have already seen that in our previous lecture. So now if we have this, let us have this as 1.5%, which is miss, and 50 is the miss penalty, and then 90% time it is clean because it is dirty for 10% of the time, and twice miss penalty will be 100, 50 into 2, which is coming down to 0.825 cycles. Now we see the memory stalls per instruction. We will just multiply the total memory accesses per instruction and the memory stalls per instruction, and we get 1.07 cycles. Thus, what will be the effective CPI? 1.1 plus 1.02, which is coming to 2.17, which is even less than the realistic write buffer if we use in our previous case when we are using write through policy. So, these are the two examples we have discussed for writing into the cache using write through and write back. Now, coming to the methods which we will be looking into some detail for cache improvement, how we can further improve the cache. So, let us consider this expression of average memory access time, which is AMAT, which is the hit time. Hit time basically is hit ratio multiplied by the access time of the cache plus miss rate into miss penalty. So, when we talk about improving the performance of this cache memory system, we can try to reduce. So, ultimately we need to reduce the average access time, average memory access time. So, either we can say that we can reduce hit time, either we can reduce miss rate or miss penalty. So, we need to see how we can take care to reduce all these parameters. In basic cache optimization techniques, we categorize the techniques into 3 categories based on the parameters I just said. Reducing the miss rate. How we can reduce the miss rate? Miss rate can be reduced by using larger block size. We can use a large block size. If we use a large block size, then if my program is pretty large and you have a large block, so the whole program is brought into some block of your cache and you can access it nicely. So, larger block size in turn reduces the miss rate. Now, how do we use miss penalty? What do you mean by miss penalty? By miss penalty, we mean that if we have multi-level cache, what happens? We bring the data from main memory into my upper level of memory, and then from upper level of memory it goes to cache. So, if we have multiple levels, and the access time of those levels will be much more less compared to access time of main memory. So, in such cases the miss penalty can be reduced by having multi-level caches. Now, reducing the cache hit time. How do we reduce the cache hit time? So, when we are hitting cache and we are searching for that tag, so we are matching something. So, from the address part, we have already seen we have certain parts for different kinds of mapping technique. If you are using set associative mapping technique, you have a tag, you have a set, you have a word. So, you need to match that tag with the number of blocks that you are having. When you are matching this tag, the CPU generates a logical address. The logical address gets translated into physical address, and then that matching takes place. Instead, can we do that once we know the logical address, from the logical address if you can extract that tag and then can directly start this matching. So, the hit time can be reduced if that can be done. So, now let us see each one of the point in some detail. When we use larger block size, what happens? So, increasing the larger block size helps in reducing the miss rate. Obviously, if you have a larger block size, the entire size of the program is, you can bring it to the same block and then you can access in a faster fashion using that. But what will happen, there must be some drawbacks as well if you have a larger cache, larger block size. So, larger block size also reduce compulsory misses. So, we have various kind of misses that also we have seen in the previous lecture. So, larger block size will also reduce the compulsory misses. So, every time you bring a data, there is a miss, but if you want to bring a data, you bring a larger block where all the data is now brought in, okay, and now you will be just hitting the cache to get the subsequent. Yeah, of course, the time will be spent in bringing the entire data from the lower level of the memory to higher level of the memory, but then you can access it very easily. But what will be the drawback? The miss penalty increases as it is required to transfer large block. It is pretty obvious. You are bringing a large block. So, for bringing a large block, there will be more number of words in that particular block. So, you have to bring all the words into your cache. So, in that particular case, you have to wait until the entire block is brought in. So, the miss penalty will increase, but in turn the hit time will increase, but the miss penalty will decrease. Miss penalty will increase. Since the number of cache blocks decreases, the number of conflict misses and even capacity misses can increase. Yes. So, conflict miss will happen, we know, for direct mapping and for set associative mapping, where different blocks of main memory is mapped to a same block of cache memory. So, in that case, this conflict will be more because you have smaller number of blocks, because the block size you have increased. If you remain the cache size limited, then the block size will be more, smaller number of blocks will be there. So, if you want to bring two blocks together, then it will be a problem. So, there it can be seen that if you have a larger block size, the overhead that we are getting might outweigh the gain. The gain which we were expecting we might not get, but it will in turn be an overhead. The overhead becomes much more. So, let us see this particular diagram showing this is the miss rate, this is the block size and this is the cache size. So, when the cache size is small, the miss rate decreases, but after certain point the miss rate again increases. Whereas, if you have a larger block size, you can see that the miss rate decreases and there is an increase, but not so much here. So, we can say that having typical, this is the cache size, having larger block size can sometime helps in reducing the miss rate. Selection of block size. So, we have seen that if you increase the block size, the miss rate will decrease. So, in such case, but other overheads will also be there, conflict misses and capacity misses will also be there. Then how do we select the block size? So, the optimal selection of block size depends on both the latency and the bandwidth of the lower level memory. So, this is somewhat is related to both the latency and bandwidth. The latency, if we have high latency and high bandwidth, this encourages large block size. If we have high latency and high bandwidth, it encourages large block size, since the cache gets many more bytes for a miss, for a nominal increase in miss penalty. So, with nominal increase in miss penalty, we get more bytes from a miss. If we have low latency and low bandwidth, this encourages smaller block size, since more time is required to transfer large blocks. Of course, more times will be required to transfer larger blocks. So, larger number of smaller blocks may also reduce conflict misses. If you have more number of blocks, then this conflict miss can get reduced. Conflict miss is where what I already discussed. So, where both the different cache memory, the different main memory blocks are mapped to a cache memory block, one cache memory block. So, in such situation, what can happen is that if you have large number of smaller blocks, so in that case you will have various opportunity of mapping different blocks to different blocks. So, that becomes easy. So, the conflict misses can even reduce. Next is use larger cache memory. So, if you have larger cache memory, then it will be easy. So, let us see how it can improve. Increasing the size of the cache is straightforward. We are saying that we will have larger block size. If the cache memory is bigger, that obviously will help. So, it is a straightforward way to reduce the capacity misses. But what is the drawback then? Increases the hit time, since the number of tags to be searched in parallel will be possibly large. So, one of the parameter is increasing. So, we are decreasing the misses, the miss rate is decreasing, but the search time for the tag in the cache memory will increase, that is the hit time, result in higher cost and power consumption. Of course, we know that cache memory is built using static RAM, which requires roughly 6 transistors for 1 bit. So, it is much more costlier compared to DRAM. If you are increasing the cache memory, you are increasing the cost as well. So, all these are related. So, which one you will reduce to how much such that you will get a better gain in turn, it is a parameter that needs to be analyzed and understood. Let us see this uses higher associativity. So, for a n-way associative cache, the miss rate reduces as we increase n. Of course, if we increase the value of n, then the associativity increases. So, this reduces the conflict misses as there are more choices to place a block in a cache. As the size of this n increases, what we can do is that more number of blocks from main memory can be placed in same set in that particular cache. So, in that way the conflict misses will definitely reduce. So, there is a general rule of thumb, a 8-way set associative cache is an effective as fully associative for practical scenario. So, it has been seen that 8-way associative cache, that means within a set we are keeping 8. So, 8 we have to do search, we have to do associatively. So, keeping 8-way set associative cache, it is effective as fully associative cache. So, we need not have to pay the cost for a fully associative cache, whereas we have seen that the requirement is up to 8-way set associative cache, it is taking care what we can achieve using n-way fully associative cache. So, a direct map cache of size n has about the same miss rate as a 2-way set associative cache of size n by 2. So, if we have a n by 2 size set associative cache, 2-way set associative cache, which will be same as direct mapping, although direct mapping will be easy to implement and all. So, what is the drawback of this? Increases the hit time as we have to search a larger associative memory, but the larger is up to 8 because we have smaller number of 8-way associativity for each of the blocks. Increases power consumption due to higher complexity of associative memory. This is another way, use of multi-level caches. Here we try to reduce the miss penalty and not the miss rate. So, we are not reducing the miss penalty, rather we are trying to reduce the miss penalty, that is the time to bring the data from your main memory to cache memory and then to processor, and not the miss rate. So, we are not concerned about the miss rate here, rather we are trying to reduce the miss penalty by use of multi-level caches. So, the performance gap between processor and memory increases with time, that we already know. Use faster cache to keep pace with the speed of the processor. We always use faster cache, and cache is always faster, such that the mismatch of speed of the processor and memory can be made smaller and smaller. Make the cache larger to bridge the widening gap between processor and main memory. We can use both in a multi-level cache system. In a multi-level cache system, by multi-level we know we have multiple number of levels. So, multiple number of levels of cache will be helpful, because we are bringing the data from main memory and we are keeping in those multi-level caches, and whenever it is required by the processor and if it is not present in L1 cache, it is looking into L2 and L3 to find out the data, and in most cases they are getting it from L1 and L2, and they do not have to go to main memory to access the data. The L1 cache can be small enough to match the clock cycle time of the fast processor. The L2 cache can be large enough to capture many accesses that would go to main memory, thereby reducing the miss penalty. So, what we are trying to say here, that L1 cache will be small enough and it will be much faster, and L2 cache will be little large enough such that most of the data from main memory, most of them are there in L2 cache, and whenever it is not present in L1 cache, I am just getting it from L2 cache and not from main memory. So, we are getting some advantage out here. So, let us consider this example. Consider a two-level cache system consists of L1 cache and L2 cache. The average memory access time can be computed as hit time of L1 plus miss rate of L1 into miss penalty of L1. Now, what is miss penalty of L1? Miss penalty of L1 is equivalent to hit time of L2 plus miss rate of L2 into miss penalty of L2. Thus, average memory access time can be written as, we just put this and we put this miss penalty L1, this particular thing in here, and we get this particular equation. So, the second level miss rate, that is miss rate L2, is measured on the leftovers from the first level cache. So, we define the following for the two level cache system here. One is called local miss rate. This is defined as the number of misses in a cache divided by total number of accesses to this cache. So, this is defined total number of misses in the cache divided by total number of accesses to this cache. So, for the first level, this is miss rate of L1, and for the second level, this is miss rate of L2. Now, what do you mean by global miss rate? This is defined as the number of misses in the cache divided by total number of memory accesses generated by the processor. So, we are not separately taking miss for L1 and miss for L2, rather we are taking in terms of total. So, this is in terms of total number of memory accesses generated by the processor. So, for the first level, this is miss rate of L1, but for the second level, it will be miss rate of L1 into miss rate of L2, because there is a miss there as well as miss there, that will be for L2, because we are considering the total. So, consider the local miss rate is large for L2 cache, because the L1 cache takes out a major fraction of the total memory access, because we are separately calculating. For this purpose, the global miss rate is more useful measure. So, we generally use this global miss rate. Fraction of memory accesses generated by the processor that goes all the way to the main memory. So, a useful measure that can be used is average memory stalls per instruction. We need to calculate the average memory stalls. The memory has to wait per instruction. So, misses per instruction in L1 into hit time of L2 plus misses per instruction of L2 into miss penalty of L2. That means the time required to bring it from the main memory. Now, let us see this example. Suppose that 1000 memory references are there and there are 60 misses in L1 cache and 15 misses in L2 cache. What are the various miss rates? So, total is 1000, out of which 60 misses are there in L1 and 15 misses are there in L2. Assume that miss penalty is 180 clock cycles, hit time of L1 is 1 clock cycle and hit time of L2 is 12 clock cycle. What will be the average memory access time? Ignore the impact of writes in this case. Let us see. Miss rate of L1 will be 60 divided by 1000 because total we are considering, that is 6%, both for local or global. Now, miss rate for L2 will be what? Miss rate of L2 means how many misses total in L1? It's 60. Out of 60 there are 15 misses. So, 15 divided by 60. So, 25%. And global miss rate for L2 will be 15 divided by 1000. Here we are just considering 60 because 60 misses are there in L1 cache and here we are considering fully, that is coming to 1.5%. So, average memory access time will be hit time for L1 plus this multiplied by this. So, hit time of L1 is 1 plus miss rate of L1 is 6% multiplied by hit time of L2 is 12 plus miss rate of L2 is 25% into miss penalty, which is given as 180. So, finally, we are getting 4.42 clock cycles. Let us see another thing, multi-level inclusion versus multi-level exclusion. So, multi-level inclusion requires that L1 data are always present in L2 cache. Inclusion means it is included. So, in L1 we have certain data and L2 cache is the next level cache where we are saying that whatever data is present in L1 is also there in L2. That is called multi-level inclusion. This is desirable because for the consistency between I/O and caches can be determined just by checking the L2 cache. So, the I/O can just check the L2 cache and find out the data. What is multi-level exclusion? This requires that L1 data is never found in L2. That means L1 data are certain data which is there in L1 and L2 data are certain data that is present in L2, but there is no common data in between. So, that means whatever is there in L1 is not there in L2. Typically, a cache miss in L1 result in a swap of block between L1 and L2 rather than replacement of L1 block with the L2 block. So, there is no replacement, rather you are bringing a block from L2 to L1. This policy prevents wasting space in L2 cache. Why? Because we have the data which is there for L1, we have separate set of data in L2. So, the space is utilized in a much better fashion compared to if we have same data in both L1 and L2. And if we require some data from which is not in L1, we have the probability that we definitely will get in L2 because the data are different, both are totally different. So, this policy prevents wasting of space in L2, may make sense if the designer can only afford a L2 cache that is slightly bigger than the L1 cache. Now, giving priority to read misses over writes. So, this is also something because we know that read are more frequent. The presence of write buffers can complicate the memory accesses. The buffers may be holding the updated value of the location needed on a read miss. So, whenever there is a read miss, the buffer may be holding an updated data. the simplest solution that is there is to make the read miss to wait until the write buffer is empty. So, it has to wait until the write buffer becomes empty. So, as an alternative, what can be done is check the content of the write buffer for any conflict. If there is any conflict, we have to check the write buffer, and if none, the read miss can continue. If there is a conflict that the data which we are trying to read is in the write buffer and has not been written, then there is a problem. So, this reduces the miss penalty to some extent. Most desktops and servers follow this approach, giving priority to reads over write, because read is much more common operation. Another is avoiding address translation during cache indexing. As I said that whenever we are CPU is generating a logical address, the logical address is first translated into physical address, and then we extract the tag bits which is matched, and finally we see that whether the data or instruction is present in cache memory or not. Instead, can we avoid that? So, even a small and simple cache must cope with the translation of virtual address to physical address to access memory. So, this has to be done. So, as an idea to make the common case fast, what can be done? We use virtual addresses for cache, since hits are much more common than misses. Such caches are termed as virtual caches. So, we will have some virtual caches in place to make the common case fast. But what is the drawback then? So, we are saying that we will not be having a translation, rather we will be extracting the address from the logical address only. So, page level protection is not possible. This is a drawback. And context switch and I/O that uses physical address further complicates the design, because this I/O and the context switching, that means switching between two processes, is required often. So, that process becomes more complicated. These are some additional cache optimizations, like to use small and simple first level caches to reduce hit time, wave prediction to reduce the hit time, pipeline caches access to increase cache bandwidth, multi-banked caches to increase the cache bandwidth, critical word first and early restart to reduce the miss penalty, compiler optimization to reduce miss rate, and prefetching of instruction and data to reduce miss penalty or miss rate. So, these are some more cache optimization technique. We already discussed many cache optimization techniques through which we can reduce hit time, miss penalty and miss rate. So, these are also some more methods through which this miss rate, hit time and miss penalty can be further reduced. So, we are in the end of lecture 32 and we are done with memory system. So, in the memory system, particularly in this week, what we have seen is, we have seen the various kinds of techniques through which we can further increase the improvement, further reduce the memory access time. So, we are trying hard to make some schemes, some methods such that the access time of the memory can be reduced, such that it can bridge the speed gap between the processor and the memory. Thank you.